topic of magnetism, we will discuss in this the first point that are what are natural magnets. So there are certain stones that we get in the nature which are naturally magnetic in nature. So those are like lodestone. There is a ore of iron which behaves like a magnet, and then there are material which are made into magnet. Okay, so those are like bar magnet, horseshoe magnet, magnetic needle, magnetic compass. So those are categorized as artificial magnets. Okay, so natural magnets are naturally occurring stones which behave like a magnet, and artificial magnets are man-made magnets. Now, any magnet, whether it is artificial or whether it is natural, show the following property. One is the directive property. That means if there is a magnet and if you suspend it freely, it will always point in the geographical north-south direction. Now, this is because the Earth itself behaves like a magnet. So inside the Earth, there is an imaginary magnet which creates a magnetic field all around the Earth. So that is the reason why when you suspend a magnet freely, that magnet always rests in the geographical north-south direction. Okay, so this is one directive property which is useful to decide whether a substance is a magnet or not. Then attraction and repulsion property. So if you have two magnets, so for any magnet, there are two poles. One we call it as North Pole, another we call it as South Pole. So when you bring two magnets closer, they can either attract each other or they can repel each other. It depends upon which two poles you are bringing closer. So if you are bringing similar poles together, they will repel. And if you are bringing opposite poles together, they will attract. Okay. And a magnet will always have two poles. That means if you break a magnet, then the other end will acquire the opposite pole, and that continues till you go to the atomic level. So magnet is always dipolar. That means it has two poles. Okay. The next point we will study is induced magnetism. So induced magnetism means, like this particular experiment, if this is a bar magnet, okay, which has a north and south pole, and an iron nail is closer to the magnet, then this iron nail is present in the magnetic field of the bar magnet. And this magnetic field of the bar magnet will induce magnetic property inside the nail. So the nail is going to acquire a pole of opposite nature to the side which is closer to the magnet, and pole of similar nature to the side which is away from the magnet. So because the nail is present in the magnetic field of the bar magnet, the nail has acquired magnetic property. So this magnetic property that the nail has acquired is called as induced magnetism. Now, this end of the bar magnet is south. Now this end of the nail behaves like north. So therefore, this particular nail will now get attracted toward the magnet. So this is why it is said that induction will precede by attraction. Okay. So in the same way, if you stick another nail, that nail will also behave like a magnet and will be able to attract other nails. Okay. So this property of the magnet to make other magnetic substance behave like magnet is called as induced magnetism. Okay. Now, the moment you remove this nail from here, you will see that all these, remove the bar magnet from there, you will see that all these nails will collapse. That means these nails behaved like magnet only in the presence of another magnet. The moment you remove that, the nails will stop behaving like a magnet and they will collapse. So therefore, these induced magnetic property is temporary. Okay. So in temporary, remember, if it is soft iron does get magnetized easily. But if you remove the source of the magnetic property, it will lose that magnetic property also equally fast. And then on the other hand, if you have substance like steel, which acquires a magnetic property, and it will not lose the property easily. Okay, so if you have kept steel in the contact of magnet, the steel will behave like a magnet, and then the steel will lose the magnetic property, okay, slowly, gradually, not as immediately like a soft iron. Moving ahead, you have lines of magnetic field. Now, this magnetic field that we spoke about some time back. So any magnet around it has an imaginary space where that magnet will, interact with other magnetic substance. This is called as the magnetic field of the magnet. Okay. Now, to represent the magnetic field, we draw some lines. Now, those lines are called as magnetic field lines. To visualize these lines, there are ways which we have adopted. One of them is this. So when you take a bar magnet and on the bar magnet place a paper, and on paper you sprinkle iron filings and then gently tap it, you will see that the iron filings arrange themselves in this pattern. So this pattern is of a magnetic field. This pattern is of a magnetic field. So we have magnetic field which is like this. So here you should notice that closer to the magnet, especially at the poles, these magnetic field lines are crowding. Okay, so this is also an example of non-uniform magnetic field. Okay, while if you see a small space over here, you will see that these lines are almost parallel to each other. This is an example of uniform magnetic field. So therefore, if you are asked to draw a uniform magnetic field, what will you show? You will show parallel lines which are pointing in the same direction. And when you have to show a non-uniform magnetic field, you will see that they are crowding. Okay, the magnetic field lines are crowding over here. And if you draw a small space, the magnetic field lines are not uniform. So this is a non-uniform magnetic field, and this is a uniform magnetic field. Fine. Okay, so these are magnetic field lines. What you need to know is properties of magnetic field lines. Okay, so there are some properties, some of them I will discuss with you. The magnetic field lines are continuous loops. So the loops, it starts from the north and ends on the south on the outside, but the inside of the magnetic field line is going from south to north. So outside it is going from north to south, inside it is going from south to north. These field lines apply lateral pressure on each other. So you can see this, they apply lateral pressure on each other. So that explains repulsion. The field lines act like a rubber band and they are contracting. So that explains attraction. So these lines are going to contract and therefore they are going to pull the magnet closer. Okay. Another property of the field line is that at any point, if you draw a tangent, that will give you the direction of the magnetic field at that point. So this is the direction of the magnetic field, which is tangent to the field at that point. Okay, so based on this property, we also have that if there is a magnetic field line which is in this direction and another magnetic field shown by yellow, they cannot intersect because that means the magnetic field has two directions at the same place. So that's not possible. Okay, therefore the magnetic field lines never intersect. So you should know what is magnetic field. You should know what are magnetic field lines, and you should know the properties based on the magnetic field lines. The next question would be to draw magnetic field lines. So if they give you for this particular diagram, the question will be there is north of one magnet and north of other magnet facing each other. So that will be this diagram over here. And if you have north and south facing each other, that will be this one. Okay, so these diagrams will be asked. Fine. Any questions so far? Okay, we move ahead. The next property that you have is evidence of Earth's magnetic field. What evidence do you have that Earth has a magnetic field? So number one, a freely suspended bar magnet always points in the north-south direction is an evidence for Earth's magnetic field. If you bury an iron rod inside the ground for a few days in the north-south direction, that iron rod gets magnetized. That is an evidence that Earth has a magnetic. The evidence that bar magnets show neutral points is evidence that Earth has a magnetic field. And yes, magnetic compass needle pointing in north-south is another evidence that Earth has magnetic field. About this neutral point, we will see what it is. But before we go ahead, there is one diagram in your textbook which talks about the Earth behaving like a magnet. So imagine this to be Earth. Okay, so over here you have this as the axis of Earth. Okay, so Earth is spinning about like this. So here, this is the geographical south, and this is geographical north. The imaginary, and this is the axis of rotation of Earth. Axis of rotation. Now, the imaginary magnet that is buried inside the Earth is not perfectly along the axis of rotation, but it is slightly at an angle, which is around 17 degrees over here. So therefore, the magnetic poles are not coinciding with the geographical poles. So this particular axis is called as the magnetic axis. So this point is the equator of the Earth, whereas this will be the magnetic equator. Okay. Also, the point to note is this pole of the imaginary magnet that is inside the Earth, that pole is called as South Pole, and the other pole is called as North. Now, this is so, the reason is, that is the reason why a compass needle's north is pointing toward this. Okay, because like poles attract, sorry, like poles repel and unlike poles attract. Okay, and also at the poles, what do you observe? That the compass needle will be standing. That means it will be perpendicular to the ground. Whereas near the equator, you will see that the needle is pointing parallel to the ground. So at the magnetic poles, the compass needle will be perpendicular to the ground. Okay, so keep a practice once this particular diagram. You should know these terms. So the paragraph needs to be known. Okay, moving ahead to the neutral points. So what are neutral points? Here I have a diagram. Okay, so in my diagram here, what I have drawn, this is the Earth's magnetic field. Okay, they are pointing up. So I will show that by drawing this. So this is north. Okay, so the magnetic field line of Earth is pointing towards north. This is a bar magnet. So the bar magnet such that the north pole of the bar magnet is facing the geographical north. So you can see these lines. Okay, so these lines are going from north to south. Okay, so what are neutral points? So neutral point is a point like here you can see that it is not very close to the bar magnet. So the magnitude of the magnetic field of the bar magnet will be pointing downwards. As you can see that the magnetic field is pointing down and the Earth's magnetic field is pointing up. But the magnitude is equal, their strength is equal, and their direction is opposite. That is the reason why both the field cancel each other and the net magnetic field is zero at that point. Okay, the net magnetic field is zero at that point, and that point is called as neutral point. And these points, okay, are around the midpoint of this magnet, okay, somewhere half of the magnet, and they are on either side. So that will be like toward the west and toward the east. So this diagram is important where you by drawing crosses, okay, these crosses, you show neutral point. The next neutral point is where the south of the magnet is facing the geographical north. So what we get over here is these are the field lines. Again, the lines are going from north to south. So we will look at a place where the Earth's magnetic field is pointing up but the magnetic field due to bar magnet is pointing down. And that will happen over here, where the magnetic field lines are going downwards. And that can happen over here, where the magnetic field lines are going towards the magnet, up to down. So again, we have these points, which acts like a neutral point, where the magnitude of the magnetic field of the bar magnet, okay, is equal and opposite to that of the Earth's magnet. So they cancel each other and you get zero magnetic field. Okay, again, drawing of this diagram is important. Fine. So now we move to the next point, which is of electromagnet. Now for electromagnet, okay, so over here I have a rod and I am wrapping wire around the rod, and then we will allow current to flow in it. Okay, we can even have a rheostat so that we can alter the current. You can control the current flowing. Okay, so just a minute. Okay, so here we have positive and negative, and then we have current flowing like this. Okay, now what happens is this end, if you notice, like you have to watch it from this side, the current will be flowing clockwise. That means the current is dropping on your right and the current is rising on your left. So therefore, the current is said to be clockwise, and that face behaves like south. Okay, so this face behaves like south. Whereas if you are watching from this end, you will have the current dropping on your left. You can see that dropping on your left. And on the back of the rod, the current is rising on your right. So on your right, it is rising. On your left, it is dropping. So this behaves like north. Okay, this behaves like north. So this is N pole. So you will have to identify, whether it is north or south. One way I have told you that if you take your right hand, so your right hand is, you're holding it like this, and this particular rod, which I have drawn, that rod is assumed to be this way. Okay, this is the rod, and you curl your fingers. Okay, you curl your fingers such that the fingers are along this arrow. So your thumb points to the side. That side is considered as north, and the other side is considered as south. Okay, I will draw one more diagram for your understanding. In that diagram, I will have the current flowing in the opposite direction. So again, we will have a battery. So if I reverse the order, then we will have the current flowing like this. Okay, now how will be your hand? So I will draw the rod. This is the rod. And now I will draw the right hand. Okay, so this is the back of your hand. This is your palm. Okay, that, and in this particular case, this is the rod. Okay, so your hand is blocking the rod, and you are grabbing the rod such that how the current is flowing over here. So this time the thumb is pointing to the left. So therefore this is north and this is south. Okay, if you don't understand this, then again you can go by this logic where you're looking at the coil from the left. So when you see, when you take a water bottle like this, you take a water bottle. So this is a water bottle. Okay, so I'm asking you to imagine when you see the bottle from this side, you don't see this shape. What do you see? You see a circle. So this is what I'm telling you. This particular eye, when the eye is watching, the eye will look at this circle. It will. So what does the current say? The current is flowing anti-clockwise. So the current is going up on the right side and it is going down on the left side. So the current is anti-clockwise. That's why this is north, okay, and the other side is south. Is that clear to everyone? So this is very important for you to identify which end is north and which end is south. What else will you be asked? If you alter the rheostat such that you allow a stronger current to flow, in place of 1 ampere, if you allow 3 amperes to flow, what will it do? It will increase the magnetic field. Instead of less number of turns, if you add more number of turns, then what will it do? It will increase the strength of the magnetic field. So the magnetic field strength can be made stronger by allowing more current to flow. It can be made stronger by adding more number of turns. Okay, not coils. So don't use the word coil. Adding more number of turns, you can make it stronger. If you stop the current from flowing, the magnetic field vanishes. And if you allow the current to flow in opposite direction, you can reverse the poles. So all this can be done in this. And this is an electromagnet. Why this is an electromagnet? Because when you allow current to flow, it produces a magnetic field around it. So there is a magnetic field that is created. And in that magnetic field, if you insert a soft ion, that soft ion will behave like a magnet. And it will so behave till the current is flowing. That is the reason why it is called as a electromagnet. So there are so many things that the electromagnet can do, which a permanent magnet cannot. Like I told you about strength. Okay, I told you about poles. I told you about stop behaving like a magnet. So it can behave like a magnet and it can stop behaving like a magnet, which a permanent magnet cannot do. But there are certain similarities also. Like if you suspend the electromagnet, it will point in the north-south direction. If you bring magnetic substance closer to the electromagnet, they will get attracted to it. If you bring like poles closer to the electromagnet, they will repel. If you bring unlike poles closer, they will attract. So these all properties are common between electromagnet and permanent magnet. And the final thing is uses. So it can be used in scrapyard to remove junk. It can be used in loading, unloading in a shipping dock. It can be used to remove metal particles from wound. So these are some of the uses of electromagnet. Electromagnet is used in electric bell. It is used in DC motor, AC generator. So these are some of the uses of electromagnet. Okay. One final thing I would do is to identify the poles. So something I'll just show you quickly by drawing. We are going to understand which end will be north and which end will be south. So you have current flowing like this. Over here, the current will be flowing this way. This is something that you will need in standard 10 as well. So this is minus plus, right? So you can see that the current is flowing clockwise over here. So this will be south, this will be north. If you see, the current is flowing anti-clockwise over there. So therefore, this is north, this is south. And here the current is flowing clockwise. So this will be south and that will be north. So you need this identification. Okay, such questions will be asked. You will have to identify which end will be south and which end will be north. So that is the end of this chapter, magnetism.